Hi, I'm Yair, and I want to show you a novel user interface for static types. We'll start by just showing it with a simple code example. This is Lamdu. Lamdu is a programming environment. It currently shows an if expression with 3 holes. Holes are placeholders for missing code in incomplete programs. Underneath the holes, we see type annotations. The condition needs to be a Boolean, and the 2 branches should have the same type, denoted by the matching type variable a. Now let's see what happens if we type a string into the top branch. Lamdu now shows that the second hole should also have the type text. What would happen if we would type a number into it? This generates a type mismatch. Its type is num, but it's expected to be text. The red rectangle represents this mismatch and is called a fragment. But what if we really want a number there? Lamdu lets us insist on this type with the close bracket keyboard shortcut. This refragmented the code and placed the type mismatch on the other branch. Unlike other programming languages with type inference, which arbitrarily assign blame for type errors, Lamdu by default predictably assigns the errors to the newest code edits. As this isn't always the desired result, Lamdu empowers the user to reassign the blame to conflicting code. Before we expand on this more, let's take a step back and review common approaches to types in popular programming languages. We'll start by comparing dynamic languages like Python and JavaScript to explicitly typed languages like Java and C#. Static languages catch type errors in compile time, never in production, and the programs are also faster and more efficient. They offer type-directed completions, but they are quite verbose, and you can't do anything with the program until you fix the type errors. When type errors occur, dynamic languages provide concrete examples for values, making errors easier to decipher, while static languages like C++ and Haskell are infamous for their cryptic type errors. But what about statically typed languages with type inference? Like, for example, Haskell. These don't suffer from the verbosity of explicit static languages, but we pay for that in the propagation and misattribution of blame in type errors. How are these issues addressed in what we call steady typing? We enjoy the normal performance and static checking benefits of static types. Type information and completions are available at all times. Let us demonstrate. Here's another piece of code in Lamdu. It contains 2 holes, and Lamdu always shows type annotations for holes. Now, let's go to the Boolean hole and type in x. We got a fragment because x is a number and we need a Boolean. Note that unlike other static languages, the type mismatch is localized with a fragment, so everything is still validly typed. So we still see the expected types for holes. If we want, we can also see the types of everything. This is quite verbose, so usually we won't want to see the types as we code. And because this is Lamdu, we can also see the values. So types are steadily available even when the program is incomplete and has type mismatches. As a result, type-assisted editing is always available. And as we've also shown, the reader controls the verbosity of type information. Next, can we run code despite of type errors? Let's see. This is a simple function enumerating favorite things. Despite containing a type mismatch, we can still run code including this function. Only when evaluation reaches the mismatch, it cannot work. So we can run despite of errors. And as we've demonstrated in the beginning of the video, type mismatches have a friendly user experience. Type mismatches are localized in fragments, so there are no errors, and type-based facilities are always available. Blame is predictably assigned, and the user has full control and can reassign it easily. Now, let's discuss another important topic in the debate between dynamic and static types. This one is related to code maintenance and refactoring. When we change the type of a function, how do we maintain this change across the codebase? In dynamic languages, we better have a comprehensive test suite that will cover every usage of the function. With static types, the compiler helps guide us to all the calls that need to be updated. But when several functions change, like when updating a library, the free propagation of type information with type inference can make things complicated. Can we help the user handle the API changes? Let's see. Here we see a code example. At the top, the sum of digits function is called with the argument 1, 2, 3, 4, 5, and the result for that is 15. Below it, we see the definition of sum of digits. It uses the digits function and calls the sum function on the result of that. Let's turn off the value annotations. They are invaluable when debugging, but they also clutter the code. This is nicer to look at. Now, let's modify the digits function so that it works for any given base, not just base 10. As we've added the base parameter, a few things happened. One cosmetic thing that happened is that Lamdu's auto layout split the line so that the code fits within the width of the window. Also, as we've added the parameter, the recursive call to digits got the new parameter added to its call. After making this change, what would happen if we were to execute the code? It cannot run. This is because its evaluation calls a dependency which has changed. What does Lamdu show us here? When the sum of digits function originally called the digits function, its argument was just a number. Now it gets a number and a base. Note that before updating its type, its previous type is used for type inference in the sum of digits function, allowing everything to still be validly typed. This allows us to update the types of our dependencies one step at a time. Note that in order to do this, Lamdu invisibly stores the types of all dependencies for every definition, unlike other programming languages that only store what you see. How can Lamdu provide all these benefits? Why didn't the other languages choose this approach as well? A key difference is that these other programming languages are based on plain text files. And perhaps you've noticed already, but Lamdu is not. Lamdu is a projectional code editor. We acknowledge that past attempts at creating projectional editors have not caught on. But unlike past attempts, we focus on also retaining the benefits of text editing. Foremost, the what you type is what you see principle. For more information on that, see our previous video. Bye for now.